How's it going, everybody? Anything fun this weekend? Something? All right, well, hopefully it was something that made you very happy, because we're going to go into a real rapid fire moment here. I was like about a third of a class behind at the end of Friday, so I just want to kind of blast through some math. If anybody has any questions, logistics, worries about stuff, please give them to us now. Yeah?
What's the difference between like a standard deviation of the weighted variable and the entropy?
What's the difference between a standard deviation and the entropy? Well, so if we're talking about classes, right, like something's a binary variable, the standard deviation and the entropy are related. I couldn't give you the math off the top of my head, but for a binomial distribution, a coin flip distribution, absolutely the entropy and the standard deviation have got to be related, because it's the probability of heads, right? Yeah? I'm sorry, I couldn't hear.
How are late days for assignment 1 going to be populated?
How are late days for assignment 1 going to be populated? So just to finish up that, I think in general the answer is it isn't always related, but it is for binomial. For late days, what's going to happen is we have a script, and GradeScope records lates, and the script is just going to keep track of your lates. And when you're out of lates, grades get modified. Okay? Any other questions? No? Okay. So where did we leave off? We left off with the idea of regularization just being introduced. Regularization is this concept that your loss function now has not just the term you're used to, the thing you're trying to explicitly minimize, like, sum of squared errors. We also have a secondary term, which is about the magnitude of the weight vector. This other term, the magnitude of the weight vector, that is regularization. By limiting the magnitude of the weight vector, we can limit how much coefficient gets assigned to every variable. And by limiting how much coefficient gets assigned to every variable, what we're limiting is the complexity of the model, right? If you have a ninth order term, but it's got fundamentally 0 weight on it, well, you don't really have a ninth order model, do you? Okay? So that's what regularization is. When we squish the weight vector, we're squishing the complexity of the fit. Okay? Now, we can squish that complexity in a multitude of different ways. This one right here is using the Euclidean norm. And the Euclidean norm squishes all of the weights variables, W1, W2, W3, W4. It squishes them all equally. Okay? There's no preference. We're just hitting all of them in equal amounts. Okay? If you want to do some math, you can figure out how to get to a closed form solution with a Euclidean weight vector. But remember this picture from, I don't remember how many pre-lectures ago? Right? This is where you can see that the Euclidean norm, the 2 norm, squishes all the weight components equally because it makes a circle in the unit plane. So when your weight vector is magnitude 1, that magnitude 1 weight vector doesn't have any squish particular to W1 or W2, right? Where, right? That's W2, that's W1, right? It's a circle. There's no particular squish there. But the L1 norm is not a circle. It's a diamond, right? Because it's x1 plus x2. or W1 plus W2. That's why it's got to be a square box or a diamond. It's a diamond because, when W2 is the entire magnitude, right, this is a 1. When W1 is the entire magnitude, that's a 1. And it's got to be a straight line in between because it's W1 plus W2. Yeah?
What's lambda?
Say again?
What's lambda?
We'll get to that in a second. Okay? But fundamentally, it's a parameter. And it's going to be a number that's less than 1. Okay? So L1 norms, they're going to try to drive you towards zeros, right? If you're like around here-ish, you're getting pretty close to a 0 W1. There's a force when one of your weight components is close to 0. It's going to tend to get driven all the way to 0. Okay? Whereas that wouldn't be true for a W2 norm. So W1-driven norms, when parameters like the ninth order term are already small, it will tend to have more force to drive them to 0. L1 norms tend to sparsify a model. They tend to drive values to 0. And when they drive values to 0, that means that we can get rid of terms in a complex model completely. L1 penalized regression models are a classic way that people do feature selection, where they say, I've got 200 variables, and I don't know which of these 200 variables are good at prediction. So I'm just going to throw all of them in a regularization model. And my linear regression plus regularization is going to do some stuff. And at the end of the day, if any of these parameters have close to 0 weights, I'll just throw them out of the model completely. Okay? It's a way to select a subset of features that might be important to your problem. It's very commonly used in both statistics and machine learning. L1 penalized regression has a special name for that reason. It's called the lasso. Right? Statisticians will refer to it as the lasso. Least absolute shrinkage and selection operator. The selection means feature selection, variable selection, right? Figure out the subset of your variables that's important. Now you may ask yourself, well, if I can do L1 penalized regression and I can do L2 penalized regression, ¿por qué no los dos? Sorry, there wasn't a lot of eyeballs that know that joke. Okay, why not both, right? Why don't we just go ahead and combine them? And you can indeed do that. That's called the elastic net. So let's go back to the earlier question. What is lambda? What is alpha? Why do we have these parameters? These are mixing parameters. They just vary the strength of the squish. So the lambda here, that number's got to be less than 1. And when that number is a very tiny number, we do a little bit of squishing. And when that number gets close to 1, it means that squishing the weight vector is every bit as important as minimizing error, right? Because there's two terms here. There's the minimize the residual sum of squares, and there's this, minimize the magnitude of the vector. So when lambda is close to 1, we care equally about minimizing the solution's vector as we do about minimizing the solution's errors. That's why generally lambda is a number much less than 1. Make sense? Okay. With the elastic net, which is a mix of different penalties, of the L1 penalty and the L2 penalty, we have the overall importance parameter, lambda, how much we want to squish, but we also have this mixing parameter, alpha. When alpha is close to 1, we're doing all L1 penalization. When alpha is close to 0, we're doing all L2 penalization. So what we have here is we're introducing you to the very first time what's called a hyperparameter. Okay? Lots of algorithms have hyperparameters. Hyperparameters are like, you ever like sit down in front of a mixing soundboard or like, you know, your stereo system, like any of your parents have like these giant enormous stereo systems with a turntable and whatever, a bunch of amps, okay? There's knobs and sliders, okay? Hyperparameters are knobs and sliders. They're not the solution themselves, but they change how the solution forms, okay? W terms, the weights, those are the parameters of the solution. They're the weights that we finally come to solve the problem with. But the hyperparameters, like lambda, they're going to change the answer in the W's. A different setting is going to change where we end up. Okay? Hyperparameters are something you tune. There are principled ways of tuning hyperparameters, like cross-validation. And we're going to talk a lot more about that. But fundamentally, this is validation, right? It's a kind of model selection. Changing the parameter, changing the hyperparameter is going to be, we're going to try it, okay, we're going to try it with the volume knob down here, and we're going to see what it looks like on the validation set. And then we're going to move the volume knob over here, and we're going to see what the error is like on the validation set, and we're going to try here. And we're going to compare those 3 values, or those 300 values, however many we're doing, on the validation set. And we're going to pick the best one on the validation set. Capiche? All right. We're going to talk more about this. Don't worry, it's not the only time. So let us look at the effects of regularization. If you open up the notebook, which is linked in the lecture notes from Friday that I never got to and I don't have time to do, you should play with this yourself. I don't have time in class today, okay? On your own. You can do this stuff here, right? 2 times ago, we showed you, hey, look, here's a 0th order model, here's a 1st order model, here's a 3rd order model, here's a 9th order model, right? We did that kind of stuff. And we know the 9th order model is overfit. And if you're looking at the sinusoidal data set, the last time we did linear, this time I've got a sinusoidal data set up, okay? Yeah, probably the 3rd is what your eyeball would pick. And if you look at validation set performance, that's also what you're quantitatively going to pick. But check this out. Here is L2 regularization on a regressor, okay? All 4 of these panes are 9th order models. In this case, the lambda is 10 to the minus 9. It's a very tiny number. So effectively, there's almost no regularization, okay? Almost no regularization. The fit, yeah, it looks pretty much like the 9th order model. Right? Not identical, but close. Okay? This is 10 to the minus 6, and already this 9th order model looks a lot more like the 3rd order model. Right? It doesn't look overfit to hell and gone. Here, 10 to the minus 3, it's pretty nice. And at 10 to the minus 1, at just, lambda equal to 0.1, at this point, we're getting pretty close to linear behavior. Right? So this goes to show you that regularization, strong regularization, penalizes complexity of fit. And you can have an overly complex model form, but squish the weights hard, and it looks more like a linear model, okay? Or something even simpler. Okay? This is regularization. Regularization is fundamentally the idea that you want to penalize over complexity because probably there's too much noise in there. In things with explicit loss functions, this almost always takes the form of an L2 or an L1 on the weight vector. Okay? There are other forms of regularization with things that are not minimized loss functions that you'll find out there, like we're going to talk about in just a couple of slides. But usually it looks like this. The math is always the same. Okay, the last thing I wanted to add is this idea that so far, just with regression itself, what we've been doing is actually an L2 norm, right? The residual sum of squares is a squared error. An L2 norm is a squared thing. All we're doing is just taking that E vector, the residual vector, and we're doing L2 on it. That is residual sum of squares to almost, right? So if you square the residual sum of squares, that is exactly equal to L2. I thought I had this. Okay, I do. I have it right here, right? So this is your ordinary least squares, right? Residual vector transpose multiplied by residual vector. Well, that's just the L2 norm on the residual squared. L2 squared is residual sum of squares. Okay? So when you have outlier data points, right? Like this or this, who knows which one of these is an outlier. But outliers with a squared term, right? The residual is squared, so an outlier is squared importance, so that its big, long lever arm to move the solution gets even longer because that residual is squared. So outliers have a lot of influence with plain old OLS with an L2 norm. Now, what if we, instead of using an L2 norm squared as our loss function, what if we just use the L1 norm of the residual vector? Now an outlier has much less pull because its residual doesn't get squared, and you tend to reject outliers. Regularization with L1 on the residual, not on the weights. On the weights, it's a regularization. On the residual vector. L1 on the residual vector can be used for robust regression, for regression where we know our data points have outliers that we want to ignore a little bit, right? They don't have no influence, they just have less influence. And you'll tend to get solutions that cluster where most of your data is, ignoring some of the outliers. So this is called robust regression. So we have now confused the shit out of everybody here. I just want to make super clear. Vector norms are a tool. We can use them on the penalty term to squish and regularize and penalize model complexity. Or we can use them on the residuals term, where what they're doing is they're showing how we are going to choose to pay attention to a displacement of the weight parameter, right? Like, are we going to take that outlier and really haul up the line of regression towards it, or are we going to ignore it a little bit? So the residuals term and the weight magnitude term both can have an L1 or an L2. Okay? In both cases, an L1 is that Manhattan distance. It's put the absolute value of the elements added together. In both cases, the L2 is the square root sum of squares, right? So I'm not going to go through this. You can, if you haven't already, go through the example of robust estimation with an L1 norm, okay? But I'm I'm going to skip all of my bad slide animations. Okay? So now the thing about L1 that I guess I probably just skipped right by is this. The shape of L1 is that, right? Just like we saw earlier in the unit vector of squishing weights with L1, it's got corners, right? L1 has corners. That is an undefined. And that is exactly where the optimum is. There is no derivative defined on a corner. That's not a smooth, continuous function. You can't take the derivative right there. So there is no analytic solution to L1 as a loss function, as a residuals loss function. Unlike ordinary least squares with the L2, you can't just solve for it. So you've got to do gradient descent. It's your only option. The gradient is defined here. That's not a problem. In fact, the gradient's just a constant. So it's super easy, right? So the way that you do L1 penalized residual regression is by gradient descent. You can't solve for it like OLS. There's no analytic solution. We get the gradient. We take a step in that direction. Do it again until we converge. Hey, look what else showed up again. There's that lambda. Lambda is a super common notation in machine learning. It always means a parameter that's smaller than 1, right? In this case, lambda is called the step size of gradient descent, right? We figure out where the gradient is. But just remember, a gradient's always defined upwards. It's just a definition of what a gradient is. We don't want to go upwards, so we do negative gradient, and we move a small step in the direction of the negative gradient. Lambda step. When lambda is a tiny number, we take a tiny step in that direction. When lambda is a big number, closer to 1, we take a bigger step in that direction. Lambda in gradient descent is another hyperparameter. A little bit later in this, we're going to see how changing lambda and other choices in gradient descent affect solutions. Okay, so recap on robust estimation. We can either, whoa, I didn't want that. We can either do this, where we're just going to take the residuals vector, and we're, instead of doing L2 OLS, we're going to do L1. That's called robust regression, because we tend to reject outliers. Or we can use L1s or L2s or combinations out here in squishing the weight. That's regularization. Questions? Yeah.
When wouldn't you want to use an L1 or an L2 on your function?
When would you not want to do regularization? So if you're modeling, right? If you're trying to come up with a model and you think you've got the right idea of the model, you don't penalize it. If you're a statistician trying to describe the Copernican universe, the Copernican solar system, right? Remember that example? Trying to actually fit the model of how the planets actually move, not just predict well, right? Then you don't penalize because you think your model's already correct. Okay? If you're doing a Ptolemaic model with the epicycles, with the planet spinning like this as they're going around, penalize the shit out of that, because all you care about is good prediction. Okay? So then you regularize and take your over-complex model and just make sure it fits the data right. So that's roughly the use cases.
Yeah, I don't know if I missed this or not, but did you go over, like, are you supposed to pick an appropriate lambda for regularization?
Yeah, so okay, we haven't really gone into that. So lambda is a hyperparameter. It's one of those volume knobs. So we're going to see this more over time, but just imagine doing cross-validation or just train, validate, test. And for every, it's like just pick like 100 lambda values. Try 100 settings. Which one works the best on the validation set? That's the one you use. Okay? Yeah.
So, to kind of touch on the difference between L1 and L2, use cases between those two, is it kind of just, because I know you said when you do L1, it means that you weight your outliers a lot less. So it influences your actual model and your predictions a lot less. Are the use cases between those two pretty much just dependent on like the data you're using?
You've got it, yeah.
If you care about like, I don't know, I don't really have a good example for either one, but if you have a piece of data where like outliers are the thing that influence how I predict and how I will model this data, then you can do L2 because it has the outlier influence.
Yeah.
That's the idea.
So think of this, right? Like if what you care about is minimizing worst case predictions, right? Like the thing you want to squish away is that one moment where you're like 300% off on just one data point. OLS, L2 residuals, right? Because you're going to tend to reduce those huge swings. If what you care more about is that for the vast majority of cases, you get low error, and every once in a while, a 300% error is okay, L1, right? So you got to think about what you're doing. Likewise, for the regularization, not for the loss function part, but for the weight squishing part, same deal, right? If you know you want to drive things that are almost zero all the way to zero, use L1. If you don't want to throw away any weight terms at all, but you just want to minimize the ones that are not important, L2. It's all use case driven. And there's usually not a perfect answer, right? There's usually, I have some reasoning, I made a choice of model format, and that's that. Yeah.
I just a question on notation. So when we see this subscript 1 and 2, how are we supposed to visualize that? Like, what does that mean?
What does it mean to have an L1 or an L2 norm? Or
It's a subscript on like the magnitude.
Yeah. So those are L1 norms and L2 norms. So if what I want to do at this point is refer you back to pre-L6 video, I think that's right, where I went over those vector norms. Okay? Okay. Any other questions before I go on to classification? Because this is supposed to be classifier week, not regression week. Okay, it's better than Shark Week. Okay, so I already kind of showed you guys the whole idea that validation curves are model selection, but maybe I should link it up to that question, right? Like these are validation curves, right? And when we're looking at the training error, the more complex, right? This is model complexity. More complex, your training error goes down and down and down until it goes to 0. But at a certain point, your validation set error goes back up because you're overfitting, right? And that divergence shows you where the overfitting is, right? And when we're here, this is all underfit because they're moving downwards together. Now, this is model order, right? But you could just make that not degree of model, but you could make that lambda. Okay? Do the same deal. Okay. So, let's get out of this. Let's go to stumps and trees. So far, we've done regression. Regression has been a linear algebra exercise for us. Now, there are linear algebra classifiers as well, but we're going to start our classifier week with decision trees which have no linear algebra in them whatsoever. Okay? So just take a break. And this also tells you something about the nature of the algorithm. We're going to broadly divide algorithms into linear algebra algorithms, also known as parametric algorithms. All of these things, linear algebra algorithms, parametric algorithms, parametric in the sense of statistics, right? They're assuming linear relationships. They're assuming normality of at least the residuals, okay? If not the variables themselves, okay? OLS assumes normality of the residuals, right? So things like decision trees don't make parametric assumptions. Things like decision trees can fit arbitrary boundaries that are not lines. We're going to show you how. But before we can see the forest, or before we can even see the tree, we've got to start with the stump. So a stump is this. You've got, whatever, 7 variables in your data set, okay? Bunch of data points. Your job is pick which one of those 7 variables you're going to use to decide between positive class, negative class, between bird and not bird, between cancer and healthy, right? You just pick one and only one of those 7 variables. How can we pick the variable that helps us make the decision best? Well, if you have 2 classes and they look like those pictures, I think you could guess, would you rather use the right or the left to choose cancer versus healthy? Where red and blue, one of them's cancer, one of them's healthy. Right, yeah? Because it's easier to see the difference between cancer and healthy, right? There's not much overlap in those histograms. When you have good separation between classes in terms of a variable, this is a situation where there's low entropy, okay? Information entropy, we talked about it in the pre-video. It's a mathematical way to measure how easy it is to separate things, A versus B, positive versus negative. It also measures purity of a sample, right? So we could also take this and look at it. If I pull a sample, is it all one thing, or is it a mix of things? Information entropy is going to be highest when we have, we have a mix 50-50, and when we're all positive class, information entropy is low. Okay? Information entropy is also low when we're all negative class, when our sample is all one thing. Information entropy is low when it's easy to put a dividing line in and not get mixed up between positive class and negative class. And the entropy is high, things are not predictable, when you can't separate out without making a lot of errors. Okay? So your decision stump is exactly what we talked about. It's pick which one of these variables is the best for doing it, and then also find the line that gives you the best, lowest error in misclassification. Okay? So we're just going to make our decision based solely on one of the 7 variables in our data set. We're going to figure out which variable we're going to choose. We also have to choose this threshold right here. All good? Okay. So here's our example circa 1989. The same way we talk about MNIST, because it's a classic machine learning task, the zip code digits. We'll also talk about sea bass and, is it salmon? I forget. Yeah, salmon and sea bass. So way back in the dawn of machine learning, even just hooking up a camera to automatedly figure out what kind of fish something is and throw it into a different gutting line depending upon which fish it is. This was high tech, yo. Yo. I don't remember. Somewhere in this PDF, there's probably a link to that original paper. I can't remember, though. Why?
If it was British, you said it was like 1980s?
Like late 80s, early 90s, maybe.
The Brits passed like a really weird law. It's like the Salmon Act.
Okay.
Like that. And it is illegal for British people to handle salmon in an improper way.
Legal to handle salmon in an improper way. That sounds way dirtier. Okay. All right. Let's go on with the ML. So we have this kind of a system where what we got to do is we got to collect data and build by hand a decision algorithm, right? This is fundamentally a decision stump. We're going to pre-process our shitty 1980s camera, going to extract the boundaries of the fish, and from that make some measurements, like how many pixels long is the fish in our shitty little camera? What's the overall number of fins we can discern, or the overall black and white lightness, because this was definitely not a color CCD camera, okay? We're going to create our classifier based upon, again, we have like that idea, like 7 variables. Pick the one variable that's best at discriminating salmon from sea bass. Choose a threshold on that variable. That's what we're doing. So let's start with length. How many pixels long is the fish? If we make histograms of the fish, just like we were seeing on the last page, if this is the salmon histogram, salmon on average are longer than the sea bass. No, other way around. Salmon are shorter, sea bass are longer, right? And what we've got to do is we've got to pick an arbitrary threshold. So let's say threshold 5. And when we pick a 5 threshold, I would rather not do that. Okay, there we go. When we pick a threshold of 5, all fish greater than 5 are going to be called sea bass, and all fish shorter than 5 are going to be called salmon. Well, when we do that, we make a couple of mistakes, right? So here's a sea bass that's labeled as a salmon, and here's some salmon that are labeled as sea bass. Only the ones that are in green are correctly classified. So out of 50 fish, only 17 of them are misclassified. And so that's a 34% error rate, right? So in this case, our metric is what percent errors are we making? It's called misclassification error. If it's wrong, it doesn't matter whether it's a false negative or a false positive, right? Either way, it's an error, and we just count up total number of errors out over total number of data samples. Okay, so even when we find the best possible threshold, we try 5, we try 6, we try 7, we try 8, we try 9, it turns out that it's 9 where we get the lowest misclassification error, 20%, okay? And guess what? If you looked at the histograms, you could have just done this in one step, right? Because that's clearly going to be the lowest misclassification errors where the 2 histograms meet, right? Right at that point. That's got to be your lowest error. Okay? But we did it iteratively. We tried all the possible thresholds. We picked this. We never get better than 20% error. Okay, moral of this story is don't use length. It's not a good feature. So try a different feature, the overall average brightness of the pixels of the fish. Because apparently salmon are lighter, more reflective than sea bass, I guess. Okay, we got a different histogram, and you can see that it's a better separated histogram. And when you try all the possible threshold values, it turns out you can get down to a misclassification error of only 8%. So clearly, this is the variable, lightness. If you're going to use just one variable to make your decision, and only one variable, You're going to choose lightness of the fish. And you're going to choose this threshold of lightness. Yeah?
Why are we only using one sample in order to figure out what our discriminant?
Not one sample, one variable. So all the samples, all the fish, all 50 fish, but we have, length and lightness, and those are variables or features, and we're going to use just one. Okay? Does that make sense?
I didn't know we were using one fish.
Yeah, so we're using all 50 fish in our training set, I should have said. Okay? So one feature, one variable, pick the best one. And it's going to be the one that has the lowest entropy, right? It's going to be the one where the two classes are the furthest apart on the histogram with the least overlap. That's definitional of what entropy is. Okay. So this is a decision stump process. Okay? Get a training set. We have a bunch of data points, in this case 50 fish. Each fish has got a correct label because it's supervised learning. We're going to try to find a decision stump classifier. The decision stump classifier has got two parameters. J, which is just an index to which one of the features. So if we have 7 features, length, lightness, width, number of fins, is that working? All right, back on. All right, so J is just an index, tells you which one of the features we're using. In this case, J is going to point at lightness of the fish as being the better one. And then there's a threshold, and the threshold is just a hard dividing line. For lightness greater than a certain value, that's a salmon. For lightness less than that value, you're calling it sea bass. Okay? So just 2 parameters. Which variable, J, which threshold, TH. If the given data point, if its J feature is bigger than threshold, it's positive class. Otherwise, it's negative class. Pretty easy. The idea of setting J in threshold is just that we're going to minimize this thing called misclassification error. I think I went through this on a previous slide, but let me just remind you how this works. This 1, this is a vector which is equal to 1 when that is true. So what is that thing inside? That says when the true value, y, is not equal to the predicted value of the function. So when truth label does not match predicted, we get a 1. Otherwise, we get a 0. In other words, we're counting errors. This notation is just a way to show you, I'm going to count up my errors. I know it's almost easier to write count your errors than to write this kind of math, but I'm sorry, you're entering machine learning where people write unnecessary math all the time. And that's why a third of this class, at least, is just teaching you unnecessary math. I'm sorry about that. Okay, so this is just the misclassification rate, right? We sum up how many errors over all the data points, sum up the number of errors, divide by the number of data points. That's misclassification rate. Okay, it's a mathematical way to write misclassification rate. So we're going to choose the J and the threshold that minimizes misclassification rate over all choices of J and all choices of threshold. If to you this is starting to sound like an exhaustive search problem, that's because it is. This is the dumbest thing in the world you can do computationally. Literally try every combination of J and threshold value until you find the lowest rate. It is dumb, it is brute force, it is potentially computationally very expensive because it is brute force search. Yeah.
Why has nobody tried to figure out a better solution to this?
Because they have. But we're teaching you about decision stumps, which are the building blocks for decision trees. So, all right, so it looks like this. We've got fish, let's say this is lightness and this is length. Okay, we've got salmon and sea bass. And what we do is we try every single possible value of lightness, and we try every possible value of length, and we pick the lowest error, which you can do by inspection on a histogram quicker than the brute force search can, right? Because you can see that this situation is way better. You can, by eyeballing the histogram of the training, pick out where you should set that threshold. Okay. But the reason I am laboriously showing you how this stump works is because now you're ready to see trees. Because a stump is the beginning of a tree. What did we do? Okay, that's setting us up for success. We started by picking, if you're gonna force me to say just use one variable, this is the variable I want to use. Trees are making stumps repeatedly into a tree shape. My stump is going to say, greater than this length, you must be a sea bass, okay? Then I take this group of things that must be sea bass, and I split them again with another stump, trying to make fewer errors. And then I take the right-hand path, and I do that again. Maybe instead of talking, I should go over here and do this, and open my favorite demo, which you're linked to, and you can explore at your leisure, but it's a nice little kind of interactive thing, right? So if you're trying to determine from data you might get off of Redfin or Zillow or whatever, right? Can I, without looking at the address, predict where a house is located based upon features of the house, right? So if you look at New York City or San Francisco, you could pick one variable, elevation, which might determine where the place is, because San Francisco has hills and New York City is flat as all get out, except for that one rock in Central Park. Okay? So you could probably pretty much chop off anything that was over a certain altitude and say that's got to be in San Fran. Okay? But realistically, you know there's more than one variable, right? It's not just one variable, just like that question was asked earlier. Okay? So maybe we want to use combinations of variables, and each time we choose a variable, we want to draw the boundaries that makes it lowest errors in the setup. Okay? So when we're doing machine learning, quote unquote, right, we're going to pick that first decision stump, the one that gives us the best results in a single go, as altitude. Okay, but we're still going to make errors. We're still going to have things that are misclassified. All right? So we can keep recursively solving this problem. So after we've split on elevation, we can take everything that went to the left and we can find the next variable that's going to minimize misclassification error and split again on that threshold. And note that on one side of the split, we ended up picking price per square foot as getting us the lowest error, But over here, it's actually a different variable on the other side of the tree. We are splitting and going deep and doing the same algorithm, decision stump, again, and splitting and splitting and splitting recursively all the way down the line. Okay? This is a decision tree algorithm. It's recursively applying the same stump procedure until we get to some stopping criteria. I'm out of time. Go have fun in section. This is section today, right? So may the force be with you.